everybody, welcome back to our discussion of functions with me. Specifically, we're talking about one-to-one and onto functions, which is just uniqueness and existence proofs in disguise because we're specifically doing them for functions. So let's just revisit uniqueness and existence proofs real fast. For uniqueness, remember that means there's only one element that does whatever it is. And so in order to prove that, in order to do that, we would say that like if A and B both do whatever it is, then in the end we can conclude that A and B are equal. For existence, all we have to do is find an example or candidate that works. We don't care how many there are or if it always works or anything like that. We want to know, does it ever work? And that's what existence is. Okay, with these sitting in the back of our minds, let's start in on the first type of function that we're going to talk about today, which is one-to-one functions. So we say that f is a one-to-one function, or injective. That's the fancy name, but I will not be using it. If, when the outputs of two elements are equal, we get that the inputs must also be equal. We can denote this by writing a little 1-1 over the function mapping arrow, so that if we're being lazy and we don't want to write out f as a one-to-one function. Another way to think about this proof is the contrapositive. You could say that if x and y are not equal, then the outputs won't be equal either. In general, we go for this definition, but sometimes that definition doesn't cut it, and so it's nice to have this guy kind of in reserve just in case. So let's look at some examples and think about this intuitively. So we've got f is a function going from r to r. It is defined by f of x equals x squared. Is f one-to-one? So let's think about f of x is equal to 4. Will we get exactly, is there only one thing that we can try plugging in to get 4? Be like, sure, x could be 2, because then 2 squared would be 4, but we could also have that x could be -2, so then f of -2 would equal f of +2. However, we know that -2 and 2 are not the same. So this is not a one-to-one function. So let's restrict that domain. So we kind of got messed up in some, like, if we take a square root, it could be a plus, it could be a minus. But if we restrict our domain to be just positive numbers and zeros, we're not going to have, no more plus or minus square root problems. So is this function one-to-one? Yes. Because, for example, x squared equals 4 has one solution now. But how do we prove this? This is not a proof. This is an example of like, okay, I can see how that works. This is not a proof. How do we prove that? Very similar to uniqueness. You start with assuming that f of a is equal to f of b, and you will eventually work down to the fact that a is going to be equal to b. Since the inputs have to be equal, if the outputs are equal, you conclude that f is then one-to-one, because that is the definition. So let's go ahead, let's try and prove this. So we're going to start by saying, suppose there exists an element A and B that are in the real positives including 0, such that f of A is going to be equal to f of B. Then we can use the definition of our function. So we can say a squared will be equal to b squared. And then for the very first time, I have been harping on you guys about taking square roots and not to do it because it's dangerous stuff. Only because I have restricted this domain to positive stuff am I going to take a square root. This is no longer dangerous territory. There's no possibility of a plus or minus outcome because there is no minus allowed because of our domain. Okay. Now, take the square root of both sides. No funny business. We have gotten down. We have now concluded that A is equal to B. Therefore, F is 1-to-1. So notice this fits exactly the format of our proof. We said that f of A was equal to f of B. We were able to get down to A is equal to B. And then from there, we conclude that f is 1-to-1. All right, next kind of function that we have to talk about is onto. So we say that f is an onto function, or surjective, which is the fancy name that I won't be using, if, this is going to be some jargon, if for all B, oops, that would be a capital B, if for all B in B, there exists an A such that B is going to be equal to f of A. This is very fancy wording for saying every element in B is going to get mapped to. So like, I guess I have an example coming up. I'm going to finish this definition. We can denote it as f is onto by putting an onto over the arrow. And then just another way to think about this, the image of A is all of B. Remember, the image would be where things get mapped to. But not going to talk about that too much right now. I feel like this is the definition that most people think of. It's much more intuitive. For example, let's go back to our x squared example. We love him. We say that f from R to R is defined by x squared. Is this onto? The answer is going to be no, because f of x will never be equal to something like -4. Unless you stick a complex number in, which we're not doing complex numbers. None of that funny business. So it's never going to hit the negatives. So we're not onto. We did not map to everything in B. So next example, we're going to restrict it. And we're just like, okay, fine. What about just like 0 to all the positive things? What about that? Well, we know what the graph looks like. We know it looks like this. We can clearly see it's going to go up forever. It's going to hit all those positive numbers. We know that the vertex is here at 0, 0. So we know it's good. But how do we formally prove that? This is the same thing as existence because right here, there exists an A. We have to go find a candidate that's going to work for each B, where B is some arbitrary number. So how do we do this? So we start with some random element that is in B, and then we eventually work down, probably using some algebra, to find the A that works so that f of A will equal B. Since B was arbitrary, that means it works for all the B's, therefore f is going to be onto. So let's go ahead and run through this proof real fast. So just like the template, we say let B be an element of B. Then we can say that the square root of B is an element of R. Yes, I am taking a square root. It is okay because this is an existence proof. Sure, I could have plus or minus going on, but I just need to find one time that it works in order to prove existence. So I'm only going to just think about the positive square root. Okay. Oh, it's not in B. It's in R0 plus. And that's what's going to let us take a square root because we're not taking square roots of negative numbers. Okay. So f of the square root of b will be equal to square root of b squared, which is b. So then there exists a, specifically equal to the square root of b, that is in our domain, such that f of a equals b. Therefore, f is onto. Done. Again, could have been a plus or minus. If you really, really wanted, you could have gone for the minus case. Doesn't matter. I just need one candidate to exist for existence to be true. Okay, I think I have pounded this into the ground. Next up, we're going to discuss what happens when we put these two together. What if we have a function that is both one-to-one and onto? Of course, we have a fancy name for it. It's called a bijective function. And bijective is just one-to-one and onto. How do we prove it's bijective? Well, you start by proving it's one-to-one. You prove that it's onto, and then you're done. 3 easy steps, right? So let's prove that if we restrict both the domain and range to the positive numbers, including 0, that we have a bijection for x squared. So 1-to-1. Honestly, this is identical to example 2. And then onto is going to be very similar to example 4. All you have to do is change R naught plus, or R naught, R to B, and R naught plus in line 2 of the proof. And you'll be done. So we have 1-to-1, we have onto. Therefore, we can conclude that f is a bijection. Okay, those are all kind of proofy, but let's get like super proofy for a moment. Let's think about this theorem. I'm going to claim that if we have a function f and a function g, and they are both onto functions, then the composition is also going to be an onto function. So let's go ahead and prove that. Actually, after writing proof, it became obvious to me. I'm just like, wait, so what am I going to do? What do I have to do? So let's write a goal really fast. We want to show that for all C, in big C, we can find an input in A such that the function of A is going to be equal to C. Okay, that's going to give us onto. We need outputs in all of C. So now let's start our proof. So onto always says let's start with an element in the range. So let C be an element of C. Then what do we know about that? So we've got A maps to B maps to C. So this one's going to be G, this one's going to be F. I know that I can get back into the set B from little element C. So there exists a B in the B because G is onto. So everything in C is going to get mapped to by G. So I can back into the set of B. So there exists a B such that G of B is going to be equal to C because we know G is onto. But same thing goes for here. Everything in B is going to get mapped to by F because F is onto. So then there exists an A in A such that F of A is going to be equal to B because F is onto. So since we have G of B is equal to C, and same B, this B is going to be equal to F of A, we can get that G of F of A equals C just by substituting this guy in right here. Okay. So that means that we have found the A that exists. So then there exists an A in A such that G composed with F of A will be equal to C. Therefore, G composed with F is an onto function. Very satisfying. There you go. That's one-to-one and onto functions. It's really just existence and uniqueness. We've done it all before. So hopefully it's not too scary. And that's all I have for right now. So I'll see you next time.